So, next what we will do is we will dive in deeper and look at how to generalize the idea of the gradient and some other commonly used operators. Okay. So, now this gradient that we have defined, we do not have to always make it look like this, right. So, we have written grad f in terms of the 3 components, and I have already written this, I will write it again. This is how I will write it. Okay. So, note I just did a small change, I wrote the unit vectors on the left hand side for convenience. Okay. Now, you can see that there is f is appearing again and again over here in this expression. Okay. So, one act of abstraction is, okay, let us get rid of f and define a operator, right. So, I can call this gradient thing, I can call it the del operator, which is like this. Okay. So, now this operator is in need of some function to act on always. Okay. So, if I write this over here, it is incomplete in the sense that it does not tell me what it is doing on anything. It needs a force to act or a field to act on, and that field in this case is a scalar field. Okay. So, when I plug in over here grad this expression, if I take over here and put f, I get back this expression. Okay. Now, this operator over here is very much like a vector. Okay. So, it obeys the usual laws of vector calculus. So, for example, of course, we know that the gradient is there. So, I can take the dot product between 2 vectors. So, first is, let us just say gradient. Okay. So, scalar function, this is called the gradient. Okay. Divergence, so this is take the dot product between 2 vectors. So, this is like the dot product, right. So, this is a vector, this is a vector, I can take the dot product, but when one of these guys is the del operator, this act is called the divergence of the vector. So, this was dot. The other thing is a cross product, right. So, we know that I can take 2 vectors and define its cross product. So, similarly, I can take these 2 vectors and take a cross product. So, the cross product we know is in the language of vector calculus, it is called the curl of the vector A. Okay. So, we started with the gradient, we defined a del operator. That del operator is something that stands by itself. You can see it has 3 components, so it is a vector. Given a vector, I can take its dot product, it is called the divergence. I can take the cross product, it is called the curl, or I can make it act on a scalar function. So, remember, so this quantity over here is a vector, right. This quantity over here will be a scalar, right, and this quantity over here is going to be a vector. Okay. So, these are the sort of nuts and bolts in which the whole language of Maxwell's equations will be written. So, this is to give us some confidence on these operators. So, let us look at these operators now one by one. Okay. So, the first operator is the divergence. So, divergence very simply I have taken a vector A and it has 3 components. So, I am going to write it as Ax, Ay, Az. When I take the dot product, this is what I get. As we said before, this is a scalar. Okay. Now, there are some very beautiful geometric meanings of what these quantities are. So, the divergence, it sort of measures how much a vector diverges from a given point. Okay. So, this is the intuitive geometric picture. So, let's take a few examples. So, let us say that I have some point over here, let us call this the origin, and I am trying to plot a vector field like this. Okay. So, what is this vector field? This is nothing but the position vector in spherical coordinates x, y, z, those are the components. So, if I plot this from the origin, it will always be pointing in which direction? Radially outwards, right, and as I go away and away from the origin, the magnitude will increase. So, they will be represented like this. Start with, as I go further outside, I can draw longer lengths, the length of the vector denotes the magnitude, and it is always radially outwards. Okay. So, everywhere at any point in space, it is pointing outwards over here. Now, you can see that if I calculate at this point over here, the vector field is sort of diverging away from one point. So, we intuitively expect that the divergence of this vector will be non-zero. You can see it, if I take del dot A over here, what am I going to get? I am going to get x plus partial with respect to y, partial with respect to z, and that is going to be equal to 3, right. So, it is a non-zero quantity. The next example that I have is a vector field that is constant in space. So, it is constant along the z axis. So, if this is let us say the z axis, then it has constant length everywhere. No matter which point in space I plot it, this vector field is like this, right. So, it is not really diverging out from anywhere, it is sort of all flowing like a river flowing in a constant speed everywhere, it is going at the same way. So, when I do when I take the divergence of this vector field over here, what do you expect? Only first two terms are 0, I am going to be left with this, and which is 0, okay. The next example that I have is like the river, but it is catching speed as it goes along the z direction, okay. So, if this is the z axis over here, then and let us say this is z equal to 0. So, which way is it going to go? So, at z for small z its value is going to be small, let us say, and then the magnitude picks up over here, and when I go to negative z is going to change direction, again the magnitude is small, and so on. So, again this vector field has an intuitive idea that it is diverging. So, when I calculate the divergence over here, again these two guys are going to contribute nothing, and I am left with, it has unit divergence, okay. So, this gives us a very nice geometric intuition of what is going on with a vector field, okay. We are trying to get ways of quantifying, measuring what a vector field looks like, what it does. So, divergence is the first tool over here. The next quantity of interest is the curl, right. So, curl is the generalization of the cross product, and just like how we take the cross product between two vectors, we write down x, y, z, then we write down the first guy's components which are here, here and here, and the components of A go into the bottom row, okay. So, if so we can write, we all know the rules of cross product. So, if I were to write this in the component form, so let us write it in bracket form. The first component will be del y a z minus del by del z into a y. The next component will be along the y hat direction. So, that is going to be del by del z a x minus del by del x a z, and the third quantity will be along z hat. So, that quantity is going to be del by del x a y minus del by del y a x, okay. So, there is a cyclic way of doing it. When I am looking at this guy, then I take this difference. When I take this guy, this is the first guy and this, and then minus this. Similarly, when I take this guy, it is going to be this difference, okay. Those of you who rusty on this, just you can do a few practice examples yourself, it is not very hard. Now, unlike the divergence operator, the curl operator measures how much a vector swirls or how much it twists about a point. So, again keeping with the river analogy, if I have a whirlpool of water, that is a place where it is swirling. So, the curl is something that measures how much a vector field is swirling, okay. So, if I take a few examples over here. So, the first example is the same vector field that I had in the previous example, right. So, from the origin going radially outwards. So, does this look like a vector field that is swirling in any way? Intuitively, no, it does not seem like it is swirling anywhere, okay. So, let us confirm our intuition, let us calculate the curl of A over here, okay. So, the first component we can see is this guy over here. So, what is AZ is Z. So, d by partial with respect to y of AZ is Z, which is 0, AY is y, this is 0. Similarly, AX is x, dx by dz is 0. So, I am going to get a big fat 0. So, it is the 0 vector, and that makes sense because this vector field over here, it is not swirling, it is just, it is diverging out, but it is not swirling, it is not rotating. One other way of visualizing it is, if I put a small paddle there, will it start rotating, right? If I put a small paddle here, it will just get pushed outwards, it will not rotate about its own axis like this. Now, here is another example, this is in the xy plane, okay. So, let us draw the xy plane over here, xy plane over here. So, what does this vector field look like? So, let us take for example the x axis, every point along the x axis over here. The quantity is, or how should I draw this field over here? So, would it be correct to draw something like this? So, for example, let us take one point over here. Okay, so let us call this 1 0, right. So, this is 1 0. What are the components of this vector over here? So, it is going to be a will be minus 0 comma 1 comma 0, right. So, that is a vector of unit length pointing in which direction? Y hat, right. So, this is going to be like this. So, okay. Now, let us take one point over here. So, let us call this 1 1, right. So, x equal to 1, y is equal to 1. So, this is now which way? So, the x component is minus 1, 1, 0, right. So, that is a vector which is pointing which way? So, the x component is negative, the y component is positive, right. So, it is going to be pointing like this 45 degrees, right. So, you can keep drawing this, you are going to get a something like this. This is a textbook example of a swirl, right. So, again we can, let us calculate the the curl of this vector field over here. So, let us take the first component over here, which is here. So, Az is 0, right. So, this term is 0, Ay is x, now dx by dz is 0. So, the first component is 0. What about, now let us go to the second component over here. Ax is minus y, but the derivative with respect to z is 0, Az is 0. So, this term is also 0, okay. So, look, is our intuition in trouble? So, let us find out. So, let us take the third term over here, Ay is x, right. Now, dx by dx, that is 1 minus, and the other term is Ax is minus y, right, minus 1, right. So, minus minus becomes, right. So, this becomes 2, okay. So, this is non-zero, right, and this is the familiar your right hand curl thumb rule sort of, you can twist it along this and the curl is showing you where the vector is non-zero, okay. So, this is a twisting field. Like we can take another example over here again in the xy plane for simplicity. Now, how does this vector field look like? So, let us take some point over here 1 0, where is this pointing? Upwards over here again, right, over here. What about the entire x axis, sorry, the entire y axis? X is equal to 0 over here. So, if the function is 0 all along over here, and as I go to higher and higher values, this is going to get larger and larger. When I come to very small over here, what about this point over here? Which way will it point? It is going to point downwards, right, because x is negative, but it is always going to be pointing in the plus y direction, right. So, the direction is fixed and it is going to, okay. So, this is this third example. So, let us again calculate. So, what is your intuitive idea? Does this swirl or does it not swirl? It does not swirl. Okay. So, let us see what the answer is. So, first component Az z is, we are going to come over here, Az is 0, Ay is x. So, this term is 0. Take the second term, Ax is 0. So, this is 0, Az is 0, again I have a 0. Third term is the interesting term. So, Ay is x. So, dAx by x is dx by x, which is 1, and Ax is 0, right. So, this is actually 1, right. So, you can see that there is a swirl happening over here, right. So, these are pointing in this direction, these are pointing in this direction. Supposing I put a paddle over here like this, you can see that these forces will make this paddle rotate over here. So, our intuition is correct that this is this vector field has a swirl about it. So, the curl is non-zero, okay. So, these are traditionally terms like the curl and the divergence are terms which in high school we have been very afraid of, but you can see that they have very simple geometrical meanings. If we get comfortable with it, we can write our equation of electromagnetics in it very easily.